National Electrical Code, specifically Article 450.10, mandates a readily accessible disconnect means for transformers. Article 100 defines readily accessible as being capable of being reached quickly for operation, renewal, or inspections, without requiring those to whom ready access is requisite to climb over or remove obstacles or to resort to portable ladders, and so forth. Now, Article 450.3c offers an exception to this disconnect requirement, and it applies when transformers are protected on the primary side by overcurrent protective devices, or OCDs, that meet specific criteria. Firstly, the OCP must be located in a readily accessible location. Secondly, these OCP must provide the same level of protection as a disconnect switch would. Let's consider a scenario. A transformer is fed from a lighting panel approximately 150 feet away, with obstructions such as shelving in between. The crucial point here is whether the overcurrent protective devices, or OCDs, protecting the transformer are readily accessible. If the OCP are indeed readily accessible, and provide adequate protection equivalent to a disconnect, then the exception in Article 450.3c applies. In this case, a separate disconnect switch right next to the transformer would not be strictly required by the NEC. Conversely, if the OCP are not readily accessible, then the exception doesn't hold. Consequently, a disconnect switch would be necessary to comply with the code. The definition of readily accessible is critical here. The NEC doesn't allow obstructions that would impede quick and safe access to the overcurrent protection. If personnel would need to move items, use tools, or take significant time to reach the OCP, they would not be considered readily accessible. Now, it is important to note that even if the NEC doesn't strictly mandate a disconnect switch, installing one might still be a prudent decision. A disconnect switch offers enhanced safety and simplifies maintenance procedures. It provides a convenient means to energize the transformer quickly in emergency situations or during routine maintenance. However, installing a disconnect switch is a good practice if it is not required. Before making a final determination, a comprehensive assessment of the OCP location is essential. Verify that the OCP are indeed readily accessible and that they provide protection equivalent to a disconnect switch. Otherwise, installing a disconnect switch is mandatory to meet the National Electrical Code requirements. Always consult with a qualified electrician to assess the specific installation and ensure compliance with all applicable codes and regulations. When evaluating the location of the overcurrent protection, consider the following questions. 1. Are the breakers or fuses easily reachable without moving obstacles or using tools? 2. Can the OCP be accessed safely without the risk of electrical shock or other injury? 3. Is there sufficient lighting and clear working space around the OCP? If the answer to any of these questions is no, then the OCP are likely not considered readily accessible. In that case, installing a disconnect switch next to the transformer is necessary. The size and type of the disconnect switch will depend on the transformer's voltage and current rating. Consult with a qualified electrician to determine the appropriate disconnect switch for your application. In addition to the NEC requirements, local codes and regulations may also apply. Be sure to check with your local electrical inspector to ensure compliance with all applicable codes. Here's a breakdown of the key considerations. Firstly, readily accessible overcurrent protection. Verify that the OCP protecting the transformer are readily accessible as defined by the NEC. Secondly, equivalent protection. Ensure that the OCP provide the same level of protection as a disconnect switch would. Thirdly, safety and maintenance. Even if not required, consider the benefits of a disconnect switch for safety and maintenance purposes. Fourthly, local codes. Check with your local electrical inspector for any additional requirements or regulations. The National Electrical Code provides guidelines for electrical installations. However, it is essential to interpret and apply the code correctly in each specific situation. Consulting with a qualified electrician ensures code compliance and a safe electrical installation. Let us look at the transformer protection. Transformers are crucial components in electrical distribution systems responsible for stepping up or stepping down voltage levels to match the requirements of different equipment. However, transformers are also susceptible to faults such as overloads, short circuits, and insulation failures. These faults can lead to equipment damage, fire hazards, and potential injury to personnel. To protect transformers from these hazards, overcurrent protection devices, or OCPs, are installed on the primary and sometimes secondary sides of the transformer. These OCP are designed to interrupt the flow of current in the event of a fault, preventing further damage to the transformer and the electrical system. The National Electrical Code, or NEC, provides detailed requirements for transformer protection in Article 450. This article covers various aspects of transformer protection, including overcurrent protection, disconnecting means, and grounding. The primary goal of transformer protection is to ensure the safety of personnel and equipment by preventing or minimizing the impact of electrical faults. Overcurrent protection is the most common and essential form of transformer protection. Overcurrent protective devices such as fuses and circuit breakers are designed to interrupt the flow of current when it exceeds a predetermined value. This value is typically based on the transformer's rated current and the allowable overload capacity. When an overcurrent condition occurs, the OCP trips or blows, disconnecting the transformer from the power source. This prevents the transformer from overheating and potentially failing. The NEC specifies the maximum allowable overcurrent protection for transformers based on their rated current and impedance. These requirements are intended to provide adequate protection against both overload and short-circuit faults. In addition to overcurrent protection, transformers may also be equipped with other protective devices such as temperature sensors and pressure relief valves. Temperature sensors monitor the transformer's winding temperature and can trigger an alarm or shutdown if the temperature exceeds a safe level. Pressure relief valves are designed to relieve excessive pressure inside the transformer tank in the event of an internal fault. Disconnecting means are also an essential part of transformer protection. A disconnecting means is a switch or circuit breaker that can be used to isolate the transformer from the power source. This allows for safe maintenance and repair of the transformer. The NEC requires a disconnecting means to be installed within sight of the transformer to be capable of being locked in the open position. Grounding is another critical aspect of transformer protection. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protection device. The NEC requires transformers to be grounded in accordance with Article 250. Proper grounding ensures that the transformer's enclosure and other metal parts are at ground potential, reducing the risk of electric shock. Let's explore the different types of overcurrent protective devices used for transformer protection. Fuses are one of the oldest and most reliable types of overcurrent protection devices. Fuses consist of a metal strip or wire that melts and breaks the circuit when an overcurrent flows through it. Fuses are simple, inexpensive, and provide excellent short-circuit protection. However, fuses must be replaced after they blow, which can be inconvenient. Circuit breakers are another common type of overcurrent protection device. Circuit breakers use a mechanical mechanism to trip and interrupt the circuit when an overcurrent occurs. Circuit breakers can be reset after they trip, making them more convenient than fuses. However, circuit breakers are generally more expensive than fuses. There are two main types of circuit breakers used for transformer protection: thermal magnetic circuit breakers and electronic trip circuit breakers. Thermal magnetic circuit breakers use a thermal element to trip on overload currents and a magnetic element to trip on short circuit currents. Electronic trip circuit breakers use electronic sensors and a microprocessor to detect overcurrents and trip the breaker. Electronic trip circuit breakers offer more precise and adjustable protection than thermal magnetic circuit breakers. When selecting overcurrent protective devices for transformer protection, several factors must be considered, including the transformer's rated current, impedance, and the type of load it serves. The OCP must be sized to protect the transformer against both overload and short-circuit faults. The NEC provides detailed guidelines for sizing OCP for transformers in Article 450. It is essential to follow these guidelines to ensure adequate protection. In addition to the NEC requirements, manufacturers' recommendations should also be considered when selecting OCP. Transformer manufacturers typically provide specific recommendations for the type and size of OCP that should be used with their transformers. These recommendations are based on the transformer's design and performance characteristics. Proper coordination of overcurrent protective devices is also crucial for transformer protection. Coordination ensures that the OCP closest to the fault will trip first, minimizing the impact on the rest of the electrical system. Coordination studies are typically performed by qualified engineers to determine the appropriate settings for OCP. These studies take into account the characteristics of the transformer, the OCP, and the electrical system. Regular testing and maintenance of transformer protection devices are essential to ensure their proper operation. Fuses should be inspected periodically to ensure that they are not damaged or corroded. Circuit breakers should be tested regularly to verify that they trip correctly. Temperature sensors and pressure relief valves should also be inspected and tested to ensure that they are functioning properly. Proper transformer protection is crucial for ensuring the safety of personnel and equipment. By following the NEC requirements and manufacturers' recommendations, it is possible to provide adequate protection against electrical faults and prevent costly damage. Remember to consult with a qualified electrician or engineer to ensure that your transformer protection system is properly designed and installed. The readily accessible requirement means that you can reach the transformer or its op quickly and safely. Consider a scenario where a transformer is located in a locked room. Access to the transformer requires finding the key, unlocking the door, and navigating through a cluttered space. In this case, the transformer would not be considered readily accessible because reaching it involves obstacles and delays. Similarly, if the op protecting the transformer is located behind a locked panel or requires the use of a ladder to reach, it would also not be considered readily accessible. The purpose of the readily accessible requirement is to ensure that qualified personnel can quickly and safely de-energize the transformer in the event of an emergency or for maintenance purposes. This helps to prevent electrical shock, fire hazards, and other potential dangers. The NEC provides specific guidelines for determining whether equipment is readily accessible. These guidelines take into account factors such as the location of the equipment, the presence of obstacles, and the ease of access. The NEC also allows for certain exceptions to the readily accessible requirement in specific situations. For example, if the transformer is located in a vault or other secure enclosure, access may be restricted to authorized personnel only. However, even in these cases, the NEC requires that the disconnecting means for the transformer be readily accessible to qualified personnel. In addition to the NEC requirements, local codes and regulations may also apply to the readily accessible requirement. Be sure to check with your local electrical inspector to ensure compliance with all applicable codes. The readily accessible requirement is an important safety provision that helps to protect personnel and equipment from electrical hazards. By following the NEC guidelines and local codes, you can ensure that your electrical system is safe and compliant. Let's explore some practical examples of readily accessible and not readily accessible scenarios for transformers. A transformer is located in an open area on the floor of an electrical room. There are no obstructions or barriers around the transformer, and it can be easily reached by qualified personnel. In this case, the transformer would be considered readily accessible. The overcurrent protection for the transformer is located in a panel board on the wall of the electrical room. The panel board is clearly labeled, and the breakers for the transformer are easily identified and accessible. In this case, the overcurrent protection would also be considered readily accessible. Now consider a different scenario. A transformer is located in a small, enclosed room that is used for storage. The room is filled with boxes and other items, making it difficult to access the transformer. In this case, the transformer would not be considered readily accessible. The overcurrent protection for the transformer is located in a panel board that is behind a locked door. Access to the panel board requires finding the key and unlocking the door. In this case, the overcurrent protection would also not be considered readily accessible. Finally, consider a scenario where a transformer is mounted on a pole outdoors. The transformer is located high above the ground, and access requires the use of a ladder or bucket truck. In this case, the transformer would not be considered readily accessible to unqualified personnel. However, the NEC allows for exceptions in these cases, provided that the disconnecting means for the transformer is readily accessible to qualified personnel. When evaluating the readily accessible requirement for transformers, it is important to consider the specific circumstances of each installation. Factors such as the location of the transformer, the presence of obstacles, and the qualifications of personnel should all be taken into account. Remember to consult with a qualified electrician or electrical inspector to ensure that your installation meets all applicable codes and regulations. Article 450.3c provides an exception to the disconnect requirement for transformers that are protected on the primary side by overcurrent protective devices, or OCPs, that meet specific criteria. This exception is intended to reduce the need for unnecessary disconnect switches in situations where the OCP provide adequate protection. The first criterion is that the OCP must be located in a readily accessible location. As discussed previously, readily accessible means that the OCP can be reached quickly and safely without undue risk of injury. The second criterion is that the OCP must provide the same level of protection as a disconnect switch would. This means that the OCP must be capable of interrupting the flow of current in the event of a fault, preventing further damage to the transformer and the electrical system. In most cases, fuses or circuit breakers that are properly sized and coordinated will provide adequate protection. However, there may be situations where additional protection is required. For example, if the transformer is serving a critical load, it may be necessary to install a separate disconnect switch to ensure that the transformer can be quickly de-energized in the event of an emergency. When evaluating whether the exception in Article 450.3c applies to a specific installation, it is important to consider the specific characteristics of the transformer, the OCP, and the electrical system. Factors such as the transformer size, voltage, and impedance, as well as the type and rating of the OCP, should all be taken into account. It is also important to consider the potential consequences of a transformer failure. If a transformer failure could result in significant damage or disruption, it may be prudent to install a separate disconnect switch, even if the exception in Article 450.3c applies. The decision of whether to install a separate disconnect switch should be based on a careful assessment of the risks and benefits. Consult with a qualified electrician or electrical engineer to determine the best approach for your specific application. In addition to the NEC requirements, local codes and regulations may also apply to the disconnect requirement for transformers. Be sure to check with your local electrical inspector to ensure compliance with all applicable codes. Understanding the exception in Article 450.3c can help you to save money and reduce the complexity of your electrical system. However, it is important to apply the exception correctly to ensure that your transformer is adequately protected. The term overcurrent protective devices refers to components like fuses or circuit breakers. These devices are designed to protect electrical equipment from excessive current flow, which can be caused by overloads or short circuits. Overloads occur when the current flowing through a circuit exceeds its rated capacity. This can happen when too many devices are connected to the circuit or when a device malfunctions. Short circuits occur when there is a direct connection between two conductors with different potentials. This can happen when insulation fails or when a wire is accidentally cut or damaged. Overcurrent protective devices are designed to interrupt the flow of current when an overcurrent condition occurs. This prevents the equipment from overheating and potentially catching fire. Fuses are one type of overcurrent protective device. A fuse consists of a metal strip or wire that melts and breaks the circuit when an overcurrent flows through it. Fuses are simple, inexpensive, and provide reliable protection. However, fuses must be replaced after they blow. Circuit breakers are another type of overcurrent protective device. A circuit breaker uses a mechanical mechanism to trip and interrupt the circuit when an overcurrent occurs. Circuit breakers can be reset after they trip, making them more convenient than fuses. Circuit breakers are available in a variety of sizes and types to meet different protection requirements. The size of an overcurrent protective device is determined by the ampacity of the circuit it is protecting. Ampacity is the maximum amount of current that a conductor can carry continuously without exceeding its temperature rating. The overcurrent protective device should be sized to protect the conductor from overcurrent. The NEC provides detailed guidelines for sizing overcurrent protective devices. It is important to follow these guidelines to ensure that your electrical system is properly protected. Overcurrent protective devices should be installed in readily accessible locations. This allows them to be easily inspected and replaced if necessary. Overcurrent protective devices should also be properly labeled so that they can be easily identified. Regular inspection and testing of overcurrent protective devices are essential to ensure that they are functioning properly. Fuses should be inspected for signs of damage or corrosion. Circuit breakers should be tested to verify that they trip correctly. Proper overcurrent protection is crucial for ensuring the safety and reliability of your electrical system. By understanding the different types of overcurrent protective devices and how to size and install them correctly, you can protect your equipment and prevent electrical hazards. Let us discuss additional considerations for transformer disconnects. Even if a disconnect switch is not strictly required by the NEC, there are several additional considerations that may make installing one a good idea. Safety is always a top priority. A disconnect switch allows you to easily de-energize the transformer in case of an emergency, such as a fire or electrical shock. This can protect personnel from injury and prevent further damage to equipment. Maintenance is another important consideration. A disconnect switch makes it much easier to perform maintenance on the transformer. By de-energizing the transformer, you can safely inspect and repair it without the risk of electrical shock. Convenience is also a factor. A disconnect switch provides a convenient way to de-energize the transformer for any reason. This can be useful for troubleshooting problems, making modifications to the electrical system, or simply shutting down the transformer for an extended period of time. Cost is always a consideration. Disconnect switches can be relatively inexpensive, especially compared to the cost of a transformer failure. The cost of a disconnect switch should be weighed against the benefits it provides in terms of safety, maintenance, and convenience. Reliability is another important factor. Disconnect switches are generally very reliable devices. However, it is important to choose a disconnect switch that is properly rated for the voltage and current of the transformer. Code compliance is essential. Even if a disconnect switch is not strictly required by the NEC, it is important to ensure that the installation complies with all applicable codes and regulations. Consulting with a qualified electrician can help you to ensure that your installation meets all requirements. Future expansion should also be considered. If you anticipate adding more equipment to the electrical system in the future, it may be a good idea to install a disconnect switch now, even if it is not strictly required. This can make it easier to add new equipment later on. Finally, consider the specific application of the transformer. If the transformer is serving a critical load, such as a hospital or data center, it may be especially important to install a disconnect switch. This can ensure that the transformer can be quickly de-energized in the event of an emergency. The decision of whether to install a disconnect switch should be based on a careful assessment of all of these factors. By considering all of the relevant factors, you can make an informed decision about whether to install a disconnect switch for your transformer. Remember to consult with a qualified electrician or electrical engineer to ensure that your installation is safe and compliant.